Welcome back to Programming Fluency. This is section 9.4, Error Handling, and see all through this chapter. Your error messages have been vague. Error, cannot open file, tells the user what failed, not why. In this video, you will learn how C answers the question why. Let's dive in. Throughout this chapter, you have been writing little error checks. If FP is null, if fread did not return the full count, but your messages have been vague. Was the file missing? A permission problem? A full disk? Let's learn how C answers that using a mechanism called errno. This is the plan for this video. First, the errno variable, a global board that records why a call failed. Next, perror and strerror. These turn an error code into a readable message. Then two rules for errno. Check the return value first and read it immediately. After that, return code conventions, how your own functions should report failure. Finally, the go-to cleanup pattern. Release every resource on every failure path. Let's start with the big picture. Some languages have exceptions. When something breaks, they throw and the error jumps up to a handler. C has none of that. In C, every error has to travel back through a return value, a null pointer, a -1, or a count that is smaller than expected. And alongside the return value, there is a global variable that records why the failure happened. That variable is called errno. Errno is a global integer, set by library functions when they fail. It holds a numeric code that identifies the specific error, and it is declared in errno.h when a function like fopen fails. It returns a failure value, and it sets errno. This picture makes errno click. Think of errno as a single board on the wall, and every library function writes to that same board when it fails. On this side, an fopen call fails, and it writes the code int, meaning no such file or directory onto the board. But here is the catch. The very next call that fails, say a malloc, overwrites the board with its own code mem out of memory. There is only one board, and only the most recent failure survives. That is the whole reason for the two rules we are about to see. Whatever is written last is all you get, so you must read errno immediately. Each errno value has a symbolic name, and you always use the name, never the raw number. We try to open a file that does not exist. Fopen returns null, so we know it failed. Now we inspect errno. If it equals int, the file does not exist. If it equals access, permission was denied. There are others too. SPC means no space left on the device. Range means a value overflowed. These symbols live in errno.h, and they are portable across systems. The raw numbers behind them differ between Linux, Mac OS, and Windows, which is exactly why you compare against the symbol, not a number. Checking errno against every possible code by hand is tedious. The function perror, print error, does it for you. When fopen fails, we call perror with the string fopen. That is it. The output is fopen : no such file or directory. Perror prints the prefix you gave it, then a colon and a space, then the system's own description of the current errno value, then a null, and it always writes to standard error, which is exactly right for an error message. Use the prefix to say what you were trying to do. Sometimes you do not want to print immediately. You want the error text as a string, so you can embed it in a bigger message, or log it. The function strerror does that. It takes an error code, usually errno, and returns a pointer to a describing string. When fopen fails, we build our own fprintf message with the file name and strerror of errno for the reason. The output combines both. Cannot open config.txt, and the reason no such file or directory. So your message is specific because it names the file, and accurate because the system supplies the reason. One rule: do not modify or free the string that strerror returns. 2 rules keep errno reliable. Rule 1: check the return value first. A successful call is not required to reset errno, so it may still hold an old value from an earlier failure. Only trust errno after the return value has told you the call actually failed. In the code, we check fp equals null first, and only then read errno with perror. Rule 2: read errno immediately. Any later call can overwrite the board, even printf, because printf may internally set errno. So if you need to do other work before reporting, save errno into a local variable first, like int saved equals errno, and report using that saved value. When you write your own functions, report failure the same way the standard library does, so your callers already know the rules. There are 3 patterns. First, pointer functions. They return a valid pointer on success and null on failure, like fopen and malloc. Second, count functions, like fread and fwrite. They return the number of items handled. A short count from fwrite always means failure, but a short count from fread might just be the end of the file, so you use feof and ferror to tell a real error apart from a normal end of file. Third, status functions. They return 0 on success, and a non-zero value, often -1 on failure, like fclose and fseek. Pick the pattern that fits and stick to it. Return -1 on failure, return 0 on success, and your callers can check your function just like a library call. Real functions often open a file, then another file, then allocate a buffer. If any step fails, you have to release everything you already acquired. The standard C idiom for this is go to cleanup. Look at the structure. At the top, we set result to -1, assume failure, and initialize every resource pointer to null. Then we acquire resources one at a time. If any acquisition fails, we jump straight to the cleanup label with go to cleanup. If everything succeeds, we set result to 0. At the cleanup label, we release everything. Free of null is safe, and the if checks stop us calling fclose on a null pointer. Notice that closing the output file can itself fail while it flushes buffered data, so if that fclose returns non-zero, we set result to -1, and the caller learns the write was not fully saved. This is one of the few good uses of goto in C. This figure shows why the pattern wins. The happy path runs straight down the middle. Initialize, open the input, open the output, allocate the buffer, process the data, success. Every failure check branches off to the side, and they all converge on one cleanup block that handles every failure path. From there, one shared block releases exactly the resources that were acquired. The ones still null are safely skipped. The big advantage is maintenance. Adding a 4th resource means one new initialization line at the top and one new release line in cleanup. Compare that to the nested if approach, where every error path repeats the whole cleanup. A common habit is to check fopen but ignore everything after it. That is not enough. Fwrite can fail if the disk fills up, and fclose can fail too because it flushes buffered data. We check fclose's return value. If it is not 0, we report it and return failure. This is why it matters. The C library buffers writes for efficiency, so fwrite may appear to succeed while the data is still sitting in memory. The actual disk write happens when fclose flushes the buffer. If the disk is full at that moment, the data is lost, and fclose returns a non-zero value. Checking fclose is your last chance to catch a write that silently failed. Now 2 classic error handling bugs. The first is checking errno without first confirming the call failed. Here we call fopen, then immediately test whether errno is non-zero. But a successful call is not required to reset errno, so errno might still hold an old value from some earlier failure. This code can report an error that never happened or report the wrong error. The fix is the first rule again. Check the return value first. If fp is null, then errno is meaningful, and you can call perror. Never test errno on its own to decide whether something failed. The second bug is printing errors to standard out instead of standard error. Here we use plain printf for an error message, which sends it to standard out. The problem shows up when the user redirects output, for example ./tool greater than results.txt. Now standard out goes into the file, so the error message is swallowed into results.txt, and the user never sees it on the terminal. Worse, it mixes error text into the program's real output. The fix is to send errors to standard error, using fprintf with standard error as the first argument. Standard error stays on the terminal even when standard out is redirected. Let's recap. C has no exceptions, so it reports errors through return codes plus the global errno, which perror and strerror translate into readable text. Follow the 2 rules. Check the return value first, then read errno and read it immediately before anything else can overwrite it. Use perror with a context prefix for a quick message, or strerror of errno when you need the text as a string. Give your own functions clear conventions. Return null or 0 and -1 or a count. Use goto cleanup to release every resource on every failure path, which is far cleaner than nested ifs. And always check fclose on output files and send every error message to standard error. Next, you can now write complete programs that handle files, arguments, and errors. In the next chapter, you will learn how C compilation and builds actually work. The preprocessor, separate compilation, linking, and makefiles.